Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So we are going to proceed with another lecture. Probably this is my second last lecture with you. And bear in mind, you have one test with me. So perhaps you you can follow all my lecture up until now, so that you can answer my test question very good. Uh, without further ado, can we start? Alright. For this lecture, we are going to learn about material balance that involve reaction. Before this, you learn material balance, but without any reaction occur, which is we only add something, and goes what? Or we separate different things where you have one input and you have two output. So you separate between those things, those mixture, such as in distillation. Those are not involve any reaction, but in this part, we are going to consider a reaction occurred in your material balance, right? So in this topic, there's three things that you need to make sure that you able to gain, you able to understand by the end of this lecture. Actually, there's two part of this lecture. This is first part. The second part will be on Thursday. So the first part you should know. So for the first part, you're going to learn a few things, and you should able to define the stoichiometry of the chemical reaction. Second things, and you should able to identify the terminology of the reaction system. Okay. Uh, and we are going to touch a little bit on fraction conversion of limiting reactant. Okay. For the differentiate the species most balance and element material balance, we will touch on the next lecture. Alright. So basically, we are going to learn a lot about chemical reactions stoichiometry. What is stoichiometry actually? Stoichiometry is a theory that of the proportion of the chemical species with one another, meaning you have proportion between reactant and your product, or your product and your with your reactant. Okay, it is a number of ratio actually. Stoichiometric equation is a statement of the relationship between number of molecule or moles of reactants and product that involved in the reaction, such as in this example, we have sulfur dioxide plus oxygen equal to sulfur trioxide. So this is a balanced stoichiometric equation. Okay, because you can balance between your left hand side and your right hand side. See, so if you want to ensure you must ensure that your chemical equation, has a balanced stoichiometric equation. Okay, such as for the sulfur. All right, for the left hand side and right hand side. So how much you have sulfur in your left hand side is 2. Meanwhile, for the right hand side, you also have 2. Meanwhile, for oxygen, this one you have 4 plus 2, you have 6. on your left hand side, and 2 times 3, so you have also 6 oxygen on your right hand side. So this is a valid stoichiometric equation. Every time, every time you encounter equations, encounter questions that involve any reaction, please recheck the chemical equation. You have to ensure the chemical equation is balanced between right and left hand, between left and right. Okay, if you if the stoichiometric equation is not balanced, your answer will be wrong. Okay, please bear in mind. All right, next. Once you the chemical equation is balanced, then you can read the chemical equation, stoichiometric equation. Let me check that. All right. So how to read this actually? What the ratio means? Okay. So this mean actually in moles. 2 moles of sulfur dioxide plus 1 mole of oxygen will produce 2 mole of sulfur trioxide. So please bear in mind this trigonometric equation represent moles. Okay, represent moles, either gram moles, either pound moles, any unit as long as it is a moles. Okay, it's not, you cannot use kilogram, you cannot use gram. Okay, so you have to keep this in mind. Okay, the chemical equation represent the moles. Okay, not mass such as gram, kilogram, something like that, because you are going to use this until end of your final year in your plant design. So you have to ensure that you really understand what is that mean. Okay, so for the chemical, from the stoichiometric equation, you also can take out another information, which is stoichiometric coefficient, or the symbol is V. What is stoichiometric coefficient? Stoichiometric coefficient is a number written in front of the molecules or atoms or reactant or product in your chemical reaction. Okay, to balance between left and your right hand side. Okay, so from this example, the stoichiometric coefficient for SO3 for sulfur trioxide is 2. Since this is a product for this reaction, then the symbol should be positive 2. Okay, so this is the stoichiometric coefficient for sulfur trioxide. Right, so second, what is stoichiometric coefficient of sulfur dioxide? So from this equation, the number in front is 2, but since this is a reactant, so your symbol is negative 2. And the last one, what is the stoichiometric coefficient of oxygen? And from this equation, the answer is 1, and the symbol is negative since oxygen is a reactant. Okay, so that's why I said just now you need to make sure that your chemical equation, stoichiometric equation is balanced. If not, you get all the answer is wrong. Okay, all right. Next, we also have stoichiometric ratio. We also that represent a ratio of stoichiometric between two molecules or two species or two reactants in your reaction. Okay, we use the conversion factor. It can be used as a conversion factor to calculate amount of particular reactant or product. We are going to learn later. Okay, let's see the example here. Okay, what is the stoichiometric ratio of sulfur trioxide generated to the oxygen consumed? Stoichiometric ratio also look at your stoichiometric coefficient. So the coefficient for sulfur trioxide is 2. So 2 moles of SO3 generated over, since it's asking for oxygen, so we look at oxygen, to 1 moles of oxygen consumed. So this is the answer. So this is what we call stoichiometric ratio. It is stoichiometric coefficient, and this is your ratio based on your question. Secondly, what is the stoichiometric coefficient of sulfur trioxide generated to the sulfur dioxide consumed? So same, 2 moles of sulfur trioxide generated over 2 moles of sulfur dioxide consumed. Alright, so the third one, how many pound moles of oxygen react to form 200 pound moles of sulfur trioxide? Okay, so it's asking how many moles oxygen needed if you want to form 200 pound moles of sulfur trioxide. Okay, so what you have is you want to produce pound moles of SO3. What you need to times with, you have to times the ratio that have, because this one is SO3, right? So you have at the bottom here is 2 moles SO3 generated. Okay, and the, the ratio on the top is 1 mole of oxygen consumed. So you can cancel out here, you can cancel out here, and left you with 200 times 1 minus, 200 times 1 divided by 2, you have 100 pound moles of O2. So the answer is 100 pound moles of oxygen you need in order for you to produce 200 pound moles of SO3. So this is how you are going to use your ratio. Alright? Okay. So you can try this one. 1, 2, 3, 4, 5. It should be easy. Okay. Next. So next, we are going to learn about a few things, a few terms, which is limiting reactant for the first one. Okay, what is limiting reactant? It's a reactant that would run out first, or in a simple word, the reactant that will be finished first, finished in the reaction. Okay. Meanwhile, for the excess reactant, okay, there is other than limiting reactant, in short, or reactant that have something left at the end of your reaction. Okay, that is not being used to complete the reaction because another reactant is already finished. Okay, something like this: A plus B equal to C. So let's say A is your limiting reactant. Okay, at the end of the process, A will be equal to 0 because it's limiting. It's going to be used until it finishes to produce C. But for the excess reactant, it's B lah. Okay, and this one is not being used totally because it happen to have excess in your system. Okay, that is what we call as excess reactant. And the lastly is what we call a fractional excess. This is your equation or your formula to find the fractional excess of A, which is equal to moles of feed minus mole of stoichiometric, meaning this one, the one that the amount that you base on the stoichiometric equation divided by moles of A based on stoichiometric equation. Okay, and we can see it from the example later. Okay, so from this example, we have acetylene plus hydrogen equal to C2H6. Alright, so first thing first, we need to make sure is this a balanced equation or not. Okay, so we have C and H. C for the left hand side you have 2, right hand side also you have 2. So C is balanced. How about hydrogen? So you have H2 plus 4, you have 6, and the right hand side also have 6. So this equation is valid and balanced. So you can proceed to the next questions. So find the limiting reactant. Alright. So this one is another sentence that I want you to really know how to read the equation. So let's say because the equation already is stated using kilomole per hour, so we use kilomole per hour lah. So from this equation, we can read that 1 kilomole of C2H2 react with 2 kilomole per hour of hydrogen. We produce 1 kilomole per hour of C2H6. Right? So this is how you read your equation. Okay? Remember, mole, not gram or kilogram. That's wrong. Okay, next. Okay. Remember, we need to, the question asking for the limiting reactant. And the info that they gave to us, they have 20 kilomole acetylene, C2H2, and they also have 50 kilomole per hour of hydrogen. Okay, so this is what they have at the beginning of reaction. So we need to find which one is limiting reactant. So the first one, I use 20 kilomole of C2H2 as my starting point. Okay, so I book a table like this. Okay, from stoichiometric equation, so this is equal to 1 kilomole per hour. This one equal to 2 kilomole per hour. This one 1 kilomole per hour. How I got the value of 1 to 1 is based on your stoichiometric coefficient. Okay, and how I get this unit, because I directly take the unit that been used in the question. That's why I started with kilomole per hour. Okay, so since in the question stated that it has 20 kilomole per hour of C2H2, so I directly put here 20 kilomole per hour. Okay, and I scale up to 20 times lah, because originally we have one, right? So since this is scale up 20, so the rest also need to scale up by 20. So 2 times 20 we have 40, 1 times 20 we have 20 kilomole per hour. So from the equations, so 20 kilomole per hour is the same thing, because we have take this one as our starting point. And if you have 20 kilomole per hour of C2H2, the amount you need for hydrogen is only 40 kilomole per hour to complete the process. And from the questions again, stated that we have actually 50 kilomole per hour of H2 hydrogen. So you have in excess. You have excess of hydrogens. So automatically your acetylene or C2H2 become your limiting reactant. Okay, understand? Because at the end of your reaction, your C2H2 has been used totally to produce your product, but your hydrogen have left 10 kilomole per hour. Okay, understand? So this is how you determine your limiting reactant or excess reactant. So this one is excess, automatically the other one is limiting. Okay, this one is when you have two reactant only lah, because you have this one and this one uh these two reactant only, and this is your product. But if you have three reactant, then you need to ensure for each one is your limiting reactant. Okay, so the second option that I use is I'm using 50 kilomole of hydrogen. Okay, because why 50? Because it's stated in the question. So 50 kilomole per hour. So this is 50 kilomole per hour. So in order to get 50 kilomole per hour, you times with 25. Since you need 2 kilomole, since the coefficient is 2, so 2 times 25 is 50 kilomole per hour of hydrogen. So since this one is times 25, so the rest also need to times with 25. Times 25 times with 25. So 1 kilomole per hour times 25 is 25 kilomole per hour. If you want to use completely 50 kilomole per hour of hydrogen, then you need 25 kilomole per hour of acetylene. But from the equation, you know that you only have 20 kilomole per hour C2H2. So that is not enough, okay, in order for the utilize fully of your hydrogen. So from here we know that C2H2 is your limiting reactant. Once this one become limiting reactant, this one become excess reactant. Okay, this is only valid when you have two reactant. If you have three reactant, then you need to make sure for the third one lah, for the third table. Okay, alright, hopefully you can follow. Okay, next, same example, C2H2. Okay, but the question's asking for the percentage of excess. Okay, same question, but adding another questions asking for the percentage of excess. So how to find? You need to use this equation. And from the previous slide, we know that the excess reactant is hydrogen. Okay, so the equation needs hydrogen feed, amount of hydrogen feed minus amount of hydrogen that been used based on stoichiometry equation divided by amount of hydrogen that been used based on stoichiometric equation. So if want to find, if they asking for the percentage, you just 8 times 100 lah, as here. So from the equation, we know that we have 50 kilomole per hour minus with 40 kilomole. How I get the 40 kilomole? From here. Okay, because we assume at the end of the process of the reaction, we utilize fully of your limiting reactant. So if you utilize your reactant, your limiting reactant, which is 20 kilomole here, then you need 40 kilomole of H2 minus 40 divided by 40, and you get this answer. 25% of excess hydrogen excess. Okay. This one actually just repeating from the slide here. This one, fractional excess. Okay. All right. Where is it? Okay, this one actually is repeating question from the previous one. So you may omit. Okay, next we are going to learn about fractional conversion of reactant, or the symbol is F. So this is the equation. Fractional conversion equal to most reactant divided by most fat. Okay, if it's asking for the percentage of conversion, then you just directly times 100. And second thing you are going to learn about extent of reaction. This is the unit. Okay, so this one is not, sorry for the mistake. Okay, so this is the equation. Extent of reaction is equal to moles reacted divided by stoichiometric coefficient. Okay, so this is moles at initially present in the system, and this one is amount of in moles of the reaction at the end. Sorry, this one is moles of reactant or product at certain time or at the end of the reaction, and this one is mole of product or reactant at the beginning of the system, at the beginning of the process. So once this one, sorry, once you rearrange and you get this value lah. Alright, most of amount of moles of molecules or reactant or any reactant equal to the moles of that reactant at the beginning plus stoichiometric coefficient based on your chemical equation times your extent of reaction. Okay. Alright, so this we learn how you are going to use that equation, the extent of reaction. Okay, the same example, which is acetylene plus 2 hydrogen equal to C2H6. Alright, the same figure, which is 20 kilomole of per hour of acetylene react with 50 kilomole of hydrogen. If the reaction proceed to completion, how much of the excess reactant will be left? How much C2H6 will be formed? And what is the extent of reaction? So we have 3 questions here. 1, 2, 3. Alright, so in order for you to find the extent of reaction, you need to know the stoichiometry coefficient. In order for you to have a correct stoichiometry coefficient, you need to make sure this equation is balanced. Okay, we know that it is balanced just now. So I put in a table. So stoichiometric coefficient for C2H2 is -1. Why negative? Because it's a reactant. It's going to be used. Hydrogen, stoichiometric coefficient for hydrogen is -2. Okay, it is 2. Negative because it's reactant. And stoichiometric coefficient for C2H6 is positive 1. 1 because the coefficient here is 1. Why positive? Because it's going to be produced in the system, in the reaction, right? So it's positive. Okay, so we know that the general equation to find the extent of reaction is this one. Number of species equal to number mole of species at the beginning plus stoichiometric coefficient of the species times extent of reaction. So this one, since we are talking about C2H2, so I replace lah C2H2, C2H2. So the coefficient is -1, so I minus with -1. Same goes with this. For hydrogen, directly substitute your stoichiometric coefficient with -2 and this one positive. Alright, so they're asking for the how much the excess will be, the excess reactant will be. Okay, apart from before this, we use a table, right, in order for us to determine this one, in order for us to determine how much left, how much excess. this one we are going to use the extent of reaction, which is very very easy. Okay, so we know that C2H2 is the limiting reactant, hence the reaction will be occurred until this reactant finish to be consumed. Okay, so from the table just now, we know that the equation for the extent of reaction for C2H2 is this one. Okay, and then we need to find the E here, and the E actually, the E here should be the same for the three molecules here. Okay, the value is the same. Alright, so we substitute more number of mole of C2H2 equal to number of mole of C2H2 at the beginning minus 1 E. Alright, so since it said that it's finished, it will be consumed until it finished to produce your product. So at the end, your product should be, your reactant should be 0 lah for C2H2. And then equal to 20 kilomole per hour, which is at the beginning we have 20 kilomole per hour of acetylene minus 1 E. So you rearrange and you are going to get the extent of reaction equal to 20 kilomole per hour. Okay, so they're asking how much excess of reactant will be left at the end of your process. So still using the same equation, but we use for hydrogen. Since we are talking about hydrogen, how much hydrogen left at the end of the reaction. So use this equation for hydrogen. And at the beginning, you have 50 kilomole per hour of hydrogen minus 2 of extent times the extent of reaction. So from here, you get 20 kilomole. So you times 20 lah. So 50 minus 40 equal to 10 kilomole per hour. This is your amount of mole hydrogen that left at the end of the reaction after all the acetylene been consumed to produce your product. Okay, get it? Next, it also asks you for the amount of product formed. So since it's asking about the product, so we use the equation for the product lah. This one, C2H6. Alright, C2H6 equal to, at the beginning we have 0, right? Because at the beginning you only have your reactant, there is no product that present in your system, so it's 0. So so we know that from previous calculation, the extent of reaction equal to 20. Hence, at the end of your reaction, we are going to produce 20 kilomole of C2H6. Okay, all of these all of the all data we get actually based on the extent of reaction equation. So it's very important for you to know how to develop a extent of reaction equation. Okay, that's all. So you can try yourself by having this practice, test yourself too, and you will have giving the answer for test yourself once for previous one and a test yourself too. The answer is here. So please try. And if you don't get the answer, then we can discuss again. Okay, that's all from me. Thank you.